Hello everyone, welcome to my first data structures and algorithms video. We're going to be solving Tower of Hanoi algorithmically. Tower of Hanoi is a puzzle which requires you to move these disks from this pole to this pole, usually the leftmost pole to the rightmost pole. I'm sure many of these have solved this before. Personally, I would solve them sort of semi-intuitively when I was younger, but I wasn't really thinking of the puzzle in a way that could be scaled up to many more disks. Anything above 4 disks, and I wouldn't be able to solve it in the minimum number of moves. Now, intuitively, you think, of course, we're going to have to move these 2 disks to a place that doesn't obstruct this disk, which would probably be something like this. And then, where could you put this? I should probably put it over here, so we don't obstruct this number 2. And then we can put this right over here, and we've solved it. For small numbers of disks, intuition often works. You don't have to really think about it too hard. But for a computer to be able to solve this, we're going to need to break it down to its foundational building blocks and build an algorithm. Now, for starters, let's call these disks 1, 2, and 3, and let's call these poles A, B, and C. And let's define the intermediary pole of a given disk N. The intermediary pole is the pole which is neither the start or destination of this disk. So for example, for disk 3, the start is pole A, the destination is pole C. The intermediary pole would be pole B. If all disks from n-1 to 1, so in the case of disk 3, n-1 is 2 and 1 is just 1. So if all disks from 2 to 1 are placed on the intermediary pole of disk n, then disk n will be unobstructed and it will be able to move from its start to its destination pole. Now, to make this simpler, I've drawn out a simple tree with all the moves that are required to solve Tower of Hanoi with 3 disks. Now, initially, we're going to have to move disk 3 from pole A to pole C. The start is A, the destination is C, the intermediary is B. That means that we're going to have to move disk 2 from pole A to pole B, aren't we? Because the intermediary of disk 3 is pole B. So we have a whole new problem where our disk is 2, our start is A, our destination is B, and our intermediary is C. To be able to move disk 2 from pole A to pole B, we're going to have to move disk 1 from the start, which is just A, to the intermediary of disk 2, which is C. The intermediary of disk 1 is going to be B, but that doesn't matter because when we're on disk 1, we can just move it. There's nothing above it to obstruct it. So if we move disk 1 from pole A to pole C, that means disk 2 is unobstructed and we can execute this move. We can move disk 2 from pole A to pole B. And then to complete this side of the tree, we're going to need to move disk 1 back from pole C to pole B, at which point everything above disk 3 is on the intermediary pole of disk 3, and disk 3 is unobstructed and it can move to its destination pole. And then we're going to do something similar to move everything above disk 3 back on top of disk 3, which will complete the entire movement of the disks. Now, in this case, our start is pole B, and our destination for disk 2 is pole C, which means the intermediary is pole A, because that's the pole that we need to put everything above disk 2 onto to be able to move disk 2 unobstructed from its start to its destination. All we need to do is move disk 1 from pole B, the start, to the intermediary of disk 2, which is pole A. Then we can execute this move, moving disk 2 from pole B to pole C, and then we can move disk 1 back on top of pole 2. Back on top of disk 2. Now, if we want to apply this to any number of disks, this is the algorithm in essence. If we're on disk 1, if n equals 1, where n is our current disk, then just move disk 1 to disk 1's destination pole. We don't need to move anything above it. Otherwise, move disks n 1 minus 1 to 1 to disk n's intermediary pole, and then move disk n to its destination pole, and then move disks n minus 1 to 1 to disk n's destination pole. And you'll notice every time we go into one of these, we have another one of these. So for disk 3, when we go into this, moving disk 2 to 1 to disk 3's intermediary pole, disk 2 has this sort of cohesive step applied to it, where its start point is whatever the start point of disk 3 was, its end point is the intermediary pole of disk 3, and its intermediary is the pole that isn't its start or end point. Now, finally, I want you to look at the code itself. Now, this is it. Basically, this is the logic that I showed you on the Word document in code form. And this is the main recursive logic. All we're doing is we're taking a start, in this case A, and an end, in this case C, and we're taking a current disk, which is going to be 3. We're getting the mid, which is the intermediary, which is just whichever pole isn't A or C, so B. This getDest method is just taking a start and an end and returning whatever isn't the start or the end. So for instance, if the start is A and the end is B, it's returning C. If the start is A and the end isn't B, it'll return B, because that means the end must be C. Now, as you can see, if we put this side by side with our tree, we're applying the left tree, and then we're executing our move, and then we're applying the right tree. If the start is A and the end is C, then the intermediary is B. So we're applying the left tree with the start being the current start, A, the end being passed as B, the current intermediary, and the current disk being whatever the disk we're on is, which would be 3 to start with, minus 1. And then we're executing the current move. This is going to go through the entire left side of the tree first, and then we get to execute the current move, and then we do the same for the right side of the tree. And at each point, this method calls itself. It's recursive. It calls itself, and that's what makes it so simple. So if we just build this and then run it, we see that we get these steps. Now, if we were to apply these steps, move disk 1 from A to C, move disk 2 from A to B, move disk 1 from C to B, move disk 3 from A to C, no, that's unobstructed, move disk 1 from B to A, move disk 2 from B to C, and then move disk 1 from A to C. That's the minimum number of moves. And of course, the number of moves, the minimum number of moves, is going to be 2 to the n minus 1, where n is the number of disks. So it will increase, the number of moves required is going to increase quite quickly. So I'm not going to show you anything above 3, but this will work for anything. So I hope that that was a clear explanation, and I hope you can understand how we can solve the Towers of Hanoi algorithmically, recursively. Thank you very much for listening. Bye.